Have you ever wondered if you could travel through time, correct past mistakes, or gain insights into the future? This concept, the ability to leap through the ages, is a staple of science fiction, captivating our imaginations with the thrill of what-ifs and the tantalizing promise of do-overs. Yet, it's not just the realm of writers and dreamers. Theoretical physicists have grappled with this enigma, debating and dissecting the possibilities of time travel through the lens of science. While the notion of journeying to the past is still a hotly contested topic, there's a consensus when it comes to voyaging into the future. Believe it or not, it's possible. And no, you don't need a wormhole, a DeLorean, or even a TARDIS to do it. The key to unlocking this future travel lies in the fabric of the universe itself. Space and time, once thought to be separate entities, are actually intertwined in a four-dimensional cosmic tapestry. This concept, known as space-time, was first proposed by the brilliant mind of Albert Einstein. According to Einstein, time is not a constant river flowing at a steady pace, but a variable that can be manipulated. So how does this work? Well, time, as it turns out, is tied to speed. The faster you move through space, the slower time moves. This phenomenon, known as time dilation, is a cornerstone of Einstein's theory of special relativity. It's the reason why astronauts on the International Space Station age slightly slower than the rest of us here on Earth. But wait, you might ask, does that mean we can actually travel to the future? The answer is a resounding yes. Time dilation allows us to leap forward in time, albeit in small increments with our current technology. But who knows what the future may hold? So time travel isn't just a figment of science fiction, but a reality. But how does it work? Let's delve deeper. Stay tuned as we unravel the mysteries of Einstein's theory of special relativity in the next chapter of our time-traveling journey. Have you heard of Einstein's theory of special relativity? Well, this groundbreaking theory completely changed our understanding of time and space. Einstein was the first to realize that time is not constant as previously believed, but instead slows down as you move faster through space. This concept is known as time dilation. Let's delve a bit deeper into this fascinating theory. Einstein proposed that as an object accelerates and moves faster, time for that object appears to slow down. This is not simply a perception, but a physical reality, a result of how speed and gravity interact with space-time. Now, what is space-time, you may ask? Einstein coined this term to represent the fusion of 3 dimensions of space and 1 dimension of time into a single, 4-dimensional continuum. Instead of treating space as a flat and rigid platform that holds all the objects in the universe, Einstein thought of it as a curved and malleable entity. To illustrate this, imagine space as a trampoline. When you place a bowling ball, representing a massive object like a star or a planet, in the center of this trampoline, it creates a dip. This dip is what we call a gravitational field. Now, if you roll a smaller ball onto the trampoline, it will naturally move towards the bowling ball. The same principle applies to objects in space. The closer an object gets to the center of the dip, or the more massive object, the faster it accelerates. Now here's where it gets even more interesting. According to Einstein's theory, because time moves more slowly as you move faster through space, the closer an object is to the center of a gravitational field, the slower time moves for that object. So, according to Einstein, the faster you move through space, the slower time moves for you. But where can we observe this phenomenon? In the next scene, we'll explore some real-world examples where the effects of time dilation have been observed. Can you believe that time dilation is a reality that our GPS satellites deal with every day? It's true. Let's dive into the nitty-gritty of this fascinating phenomenon. GPS satellites, those diligent navigational aids orbiting our planet, are in a constant dance with time. They orbit roughly 12,500 miles above the Earth's surface and carry highly accurate clocks on board. But here's where it gets interesting. These clocks gain an average of 38 microseconds per day due to time dilation. Now you might be thinking, 38 microseconds, that's barely a blink of an eye. And you'd be right. On the surface, it seems inconsequential. But let's delve a little deeper. These satellites rely on the precision of their onboard clocks to provide accurate global positioning. A gain of 38 microseconds each day, if left uncorrected, would result in a positioning error of almost 6 miles. That's about the length of 10,000 football fields. And this error would keep on growing each day. Imagine trying to find your way home and ending up 6 miles off course. Not ideal, right? So, how do we keep our GPS systems from sending us on wild goose chases? The answer lies in the magic of technology. These satellites are programmed to correct for this time dilation effect constantly. This ensures that the time kept by their onboard clocks stays in sync with the time on Earth, maintaining the accuracy of the global positioning system. But what causes this time dilation effect? It's a consequence of Einstein's theory of special relativity. As these satellites are further from the Earth's core and moving rapidly through space, time ticks slightly faster for them compared to an observer on Earth's surface. This difference in the passage of time, albeit minuscule, is what we refer to as time dilation. So, time dilation is not just a theory, it's a part of our everyday life, but can we see it on a larger scale? Let's explore that in the next segment. Stay tuned. Remember the movie Interstellar? Let's see how it portrayed time dilation. The film, directed by Christopher Nolan, dives into the concept of time dilation in a way that's both entertaining and thought-provoking. At one point in the plot, our protagonists, led by Matthew McConaughey, find themselves on a planet with an extreme gravitational field caused by a nearby black hole. Now here's where things get interesting. Due to the intense gravitational influence of the black hole, time slows dramatically for the crew on the planet. So much so that 1 hour on the planet equates to 7 years back on Earth. This is a vivid depiction of time dilation, where time passes at different rates in regions of different gravitational potential. When the crew eventually returns to Earth, McConaughey's character finds his daughter age dramatically, while he appears to be the same age as when he left. This is a poignant reminder of the potential personal costs of time dilation, as loved ones may age and even pass away, while the time traveler remains relatively unchanged. Interstellar, while being a cinematic spectacle, does a commendable job of portraying this complex concept of time dilation in a manner that's digestible to the movie-going audience. It takes the abstract theories of Einstein and brings them to life in a tangible, albeit dramatized manner. However, it's important to remember that the movie, while grounded in real scientific principles, does take creative liberties. The time dilation experienced by the characters is far more extreme than anything we've observed in reality. Yet, it serves as an intriguing exploration of the possibilities that could lie ahead if we ever manage to harness the power of time dilation for interstellar travel. So, while Hollywood may have dramatized the effects of time dilation, the underlying science is sound. But why haven't we made such drastic leaps forward in time yet? Let's delve into that in the next segment as we explore the future of time travel. As we stand on the brink of scientific advancements, one question remains. Why hasn't humanity succeeded in making significant leaps forward in time? Well, it all comes down to velocity. To make significant leaps into the future, we would need to harness the intense gravitational acceleration caused by black holes, or propel a traveler into space at speeds close to the speed of light. That's a staggering 1 billion kilometers per hour. With our current technological capabilities, we can only manage to make minuscule jumps into the future, mere microseconds at a time. We're just not quite there yet. But let's imagine for a moment that we do reach that point, where we can send a human into the future by traveling at near light speed. A fascinating concept indeed, but it presents another conundrum. Would there be any way for the time traveler to return to the past and share their findings? Unfortunately, time dilation, as we understand it today, doesn't allow for a round trip. It's a one-way ticket to the future with no return journey. This is because time dilation works by slowing down time relative to the speed of an object's movement through space. It doesn't provide a mechanism to reverse the process and accelerate time, which would be required to travel back into the past. Now let's touch on the subject of interstellar travel at speeds close to the speed of light. It's a tantalizing prospect, isn't it? Dr. Jamie Matthews, a professor of astrophysics at the University of British Columbia, suggests that it might be possible. However, we're still a long way from turning this possibility into reality. The science of time travel is still evolving, and there are many hurdles to overcome. But every day, we inch closer to understanding the mysteries of time and space. It's a journey filled with potential and possibilities, a testament to human curiosity and our relentless pursuit of knowledge. While we may not be able to travel years into the future or return to the past yet, the science of time travel continues to evolve, and who knows what the future holds.